So here's something worth sitting with for a moment. Right now, tonight, wherever you are, you're lying in the dark, and every single atom in your body, every bit of carbon in your bones, every molecule of oxygen drifting through your lungs, all of it was once packed into a space smaller than a pinhead. Smaller than that, actually. Smaller than anything you could ever see or hold, or even really imagine. Everything that exists, every star, every galaxy, every grain of sand on every beach, every drop of water in every ocean, all of it was once compressed into an almost infinitely tiny point of unimaginable density and heat. And then, about 13.8 billion years ago, something happened. We call it the Big Bang, and honestly, that name is a little misleading, because it wasn't really a bang, and it wasn't really big, not at first. But it's the name we've got, and the story behind it is one of the most extraordinary things human beings have ever managed to piece together. So let's talk about it. Slowly, gently, one piece at a time. And let's start not with the universe itself, but with the people who figured this out. Because the Big Bang isn't something anyone observed directly. Nobody was there. There's no footage. What we have instead is a detective story, one of the greatest detective stories ever told, where the clues are faint signals in the sky, tiny shifts in the color of starlight, and mathematical equations scribbled on chalkboards in the early 20th century. And the detectives? They were a strange and wonderful collection of priests, physicists, astronomers, and misfits who, piece by piece, over decades, assembled a picture of the universe's origin that turned out to be far stranger than anything anyone had imagined. To understand how we got to the Big Bang, you have to understand what people believed before it, and for most of human history, the answer is pretty simple. People assumed the universe had always been here. It was just there, eternal, unchanging in its broad strokes. The stars moved, the seasons turned, but the cosmos itself was thought to be a fixed stage, a backdrop that had existed forever and would continue to exist forever. Even Isaac Newton, brilliant as he was, basically assumed a static, infinite universe. And when you think about it, that's a pretty comfortable idea, right? The universe just is. It doesn't need a beginning. It doesn't need an explanation for how it started. It's simply always been. Albert Einstein felt the same pull toward that idea. When he published his general theory of relativity in 1915, he'd created the most powerful description of gravity the world had ever seen. General relativity didn't just describe gravity as a force pulling objects together. It reimagined gravity as the warping of space and time themselves. Massive objects like stars and planets actually bend the fabric of space-time around them, and other objects follow those curves. It was a radical, beautiful idea, and it worked. The math was elegant. The predictions were precise. But there was a problem. When Einstein applied his own equations to the universe as a whole, they told him something he didn't want to hear. They told him the universe couldn't be static. It had to be either expanding or contracting. The math was clear. A universe full of matter, governed by gravity, could not just sit still. It would either be flying apart or collapsing inward. And Einstein didn't like that. Not one bit. He was so committed to the idea of a static, eternal universe that he actually added an extra term to his equations, a fudge factor, really, called the cosmological constant. It was essentially a repulsive force baked into the fabric of space itself, perfectly balanced against gravity, holding everything in place. It was mathematically allowed, sure, but it was also, let's be honest, a patch. a fix designed to make the equations give him the answer he wanted rather than the answer they were naturally producing. Einstein would later call this the biggest blunder of his career. But we'll come back to that, because the story of the cosmological constant has a twist ending that nobody saw coming, not even Einstein. Now, while Einstein was busy trying to keep the universe still, someone else was looking at those same equations and seeing something completely different. His name was Alexander Friedmann, and he was a Russian mathematician and physicist working in Petrograd. That's what St. Petersburg was called at the time, in the early 1920s. Friedmann was not a household name. He wasn't famous. He didn't have Einstein's celebrity or influence, but he was very, very good at math. And when he worked through Einstein's field equations of general relativity without adding that cosmological constant, he found solutions that described a universe in motion, expanding, contracting, oscillating, different possibilities depending on how much matter the universe contained and how fast it was moving. Friedmann published his results in 1922, and they were, frankly, ignored by almost everyone. Einstein himself initially dismissed them, even claiming there was a mathematical error. He later retracted that criticism. Friedmann's math was correct, but the damage was done. The idea of a dynamic, changing universe just didn't fit the prevailing worldview, and Friedmann didn't live long enough to see his work vindicated. He died in 1925, at just 37 years old, from typhoid fever. He never knew how right he was. Here's where the story gets really interesting, though. Because independently of Friedmann, working in a completely different country and coming from a completely different background, another person arrived at the same conclusion. His name was Georges Lemaitre, and he was a Belgian Catholic priest. Let that sink in for a second. One of the founding fathers of the Big Bang theory was a priest. Lemaitre had studied engineering before World War I, served as an artillery officer during the war, and then turned to physics and cosmology. He studied at Cambridge under Arthur Eddington, one of the leading astrophysicists of the day, and then at MIT. He was deeply religious, but he was also a rigorous scientist, and he saw no conflict between those two things. He believed that science described how the universe worked, and faith addressed why, and that the two questions were fundamentally different. In 1927, Lemaitre published a paper in a relatively obscure Belgian journal, which is part of why it took a while to get noticed, in which he derived an expanding universe solution from Einstein's equations. But he went further than Friedmann had. Lemaitre didn't just show that the universe could be expanding. He connected that mathematical prediction to actual astronomical observations. He looked at data showing that distant galaxies appeared to be moving away from us, and he proposed that this was exactly what you'd expect if the universe were expanding. Think about that. He took the abstract math of general relativity and linked it to something you could actually see through a telescope. That's a huge intellectual leap. And then Lemaitre did something even bolder. He followed the logic backward. If the universe is expanding now, then in the past it must have been smaller. Go far enough back, and everything must have been compressed into a single, incredibly dense state. He called this the primeval atom, a kind of cosmic egg from which everything had emerged. It was the first real articulation of what we now call the Big Bang. The universe had a beginning. It started from an almost unimaginably compressed state and had been expanding ever since. Now, you might think the scientific world greeted this idea with excitement. They did not. When Lemaitre presented his ideas to Einstein in person at a conference in 1927, Einstein reportedly told him, Your calculations are correct, but your physics is abominable. Which is a pretty devastating thing to hear from Albert Einstein, right? But Lemaitre was stubborn in the best possible way. He kept working, kept refining his ideas, and kept waiting for the evidence to catch up. And here's the thing. The evidence was already coming. It was being gathered night after night at a telescope on a mountain in Southern California by a man named Edwin Hubble. Hubble was working at the Mount Wilson Observatory near Pasadena, using what was at the time the most powerful telescope in the world, the 100-inch Hooker telescope. And what Hubble was doing painstakingly over years was measuring the distances to faraway galaxies and figuring out how fast they were moving. Now, to understand what Hubble found, you need to know about something called redshift, and it's actually a really intuitive concept once you think about it. You know how when an ambulance is coming toward you, the siren sounds higher pitched, and then as it passes and moves away, the pitch drops. That's the Doppler effect. The sound waves get compressed when the source is approaching and stretched out when it's receding. Light works the same way. When a galaxy is moving away from us, the light waves it emits get stretched out. Visible light that starts out in the blue part of the spectrum gets shifted toward the red end. So if you look at the light from a distant galaxy and you see that its spectral lines, those characteristic fingerprints of the elements it contains, have all been shifted toward the red, you know that galaxy is moving away from you. The bigger the red shift, the faster it's receding. Hubble wasn't the first person to notice that galaxies showed redshifts. An astronomer named Vesto Slipher had been measuring galactic redshifts since around 1912, working at the Lowell Observatory in Flagstaff, Arizona. Slipher's work was painstaking and brilliant, and he deserves far more credit than he usually gets. By the early 1920s, he'd shown that most of the galaxies he could measure were redshifted, meaning they were moving away from us. But Slipher didn't have good distance measurements. He could tell you how fast a galaxy was receding, but not how far away it was. And without both pieces of information, you couldn't see the full picture. That's what Hubble added, using a method involving a special type of star called a Cepheid variable. These are stars that pulse in brightness in a very predictable way, and the period of their pulsing is directly related to their true luminosity. So if you can measure how bright they appear from Earth and compare that to how bright they actually are, you can figure out how far away they must be. Using that method, Hubble was able to estimate the distances to a number of galaxies. And when he plotted galaxy distance against recession velocity, something remarkable emerged. There was a pattern. The farther away a galaxy was, the faster it was moving away from us. And it wasn't random, it was proportional. A galaxy twice as far away was receding roughly twice as fast. 3 times as far, 3 times as fast. This relationship, published by Hubble in 1929, became known as Hubble's law, and it changed everything. Because that pattern, velocity proportional to distance, is exactly, precisely, what you would expect to see if the universe itself were expanding. Not galaxies flying through space away from some central explosion point, but space itself stretching, carrying the galaxies along with it. Imagine dots painted on the surface of a balloon. As you inflate the balloon, every dot moves away from every other dot. A dot that's far away moves away faster than a dot that's nearby. There's no center to the expansion on the balloon's surface. Every point sees every other point receding. That's what's happening with the universe. And this is where it's worth pausing for just a moment, because this idea, that space itself is expanding, is one of the most confusing and counterintuitive concepts in all of cosmology, and it trips up almost everyone the first time they encounter it. When we say the universe is expanding, we don't mean that galaxies are rocketing outward through a pre-existing void, like shrapnel from a bomb. We mean that the fabric of space, the actual distance between points, is increasing. New space is, in a sense, being created between objects. The galaxies aren't really moving through space so much as they're being carried along as space itself grows, and that means there's no edge to the expansion, no center, no special point where the Big Bang happened. It happened everywhere. Every point in the universe was once that primeval atom Lemaitre described. Every point was once at the very beginning. Let that settle for a moment. It's a strange thought. The Big Bang didn't happen somewhere out there, at some specific location you could point to. It happened right where you are, and right where the most distant galaxy is, and everywhere in between. All of space was compressed into that initial state, and all of space has been expanding ever since. So by the early 1930s, the pieces were falling into place. Einstein's equations predicted a dynamic universe. Friedman and Lemaitre had shown mathematically that the universe could be expanding. Hubble's observations confirmed that it was. Einstein himself visited Mount Wilson in 1931, looked through Hubble's telescope, and finally abandoned his cosmological constant, accepting that the universe was indeed expanding. Lemaitre's primeval atom hypothesis was gaining traction, but it was still deeply controversial. Many physicists were uncomfortable with the idea of a universe that had a definite beginning. It felt too much like a creation story. It raised uncomfortable questions about what came before, about what caused it, about whether science was straying into territory that belonged to philosophy or theology, and that discomfort would fuel one of the great scientific rivalries of the 20th century. Because in the late 1940s, a brilliant, acerbic British astronomer named Fred Hoyle would propose an entirely different model of the universe, one with no beginning and no end. And in doing so, he would accidentally give the Big Bang its name. Hoyle meant it as an insult, a way to mock the idea of everything starting with a single explosive moment. But the name stuck, and the battle between Hoyle's steady-state theory and the Big Bang model would dominate cosmology for the next 2 decades. And the way it was finally settled involves one of the most beautiful accidental discoveries in the history of science, a discovery made by 2 engineers who weren't even looking for it, who thought at first that the strange signal in their antenna was caused by pigeon droppings. Seriously, pigeon droppings. That's what they thought was causing the problem. And honestly, you can't blame them, because what they were hearing made no sense at all given what they were trying to do. So let me tell you about Arno Penzias and Robert Wilson, because their story is one of those moments in science where you just have to sit back and appreciate how the universe sometimes hands you the answer to a question you didn't even know you were asking. It's 1964. These 2 guys are working at Bell Telephone Laboratories in Holmdel, New Jersey. They're radio astronomers, but they're working for a telephone company, which already tells you something interesting about mid-century American science. A lot of the most important pure research was happening inside corporate labs. Bell Labs in particular was this extraordinary place. The transistor was invented there. Information theory was born there. And Penzias and Wilson were there because Bell Labs had this enormous horn-shaped antenna, about 20 feet long, that had originally been built for a very practical purpose, bouncing radio signals off the Echo balloon satellites for early telecommunications experiments. By 1964, the satellite work had moved on, and Penzias and Wilson got permission to repurpose this antenna for radio astronomy. They wanted to measure the radio emissions coming from the halo of our own galaxy, the Milky Way. Fairly routine stuff as far as radio astronomy goes. But here's the thing. To do precise radio astronomy, you need an incredibly clean signal. You need to account for every possible source of noise: the atmosphere, the ground, the electronics in your equipment, interference from nearby cities, all of it. You subtract all the known sources, and whatever's left is your astronomical signal. That's the whole game. And Penzias and Wilson were meticulous about this. They calibrated everything. They accounted for every source of interference they could think of, and when they pointed their antenna at the sky, they found a persistent, low-level hum of microwave radiation that they could not get rid of. It was there no matter which direction they pointed. It was the same intensity day and night. It didn't change with the seasons. It wasn't coming from the sun or from any particular star or galaxy. It was just everywhere. A faint, uniform glow, corresponding to a temperature of about 3.5 Kelvin. That's 3.5 degrees above absolute zero. Now, when you're an experimentalist and you find a signal you can't explain, your first instinct isn't to declare that you've discovered the echo of creation. Your first instinct is to assume something's wrong with your equipment. So they checked everything. They rebuilt connectors. They tested the electronics. And yes, they found that pigeons had been nesting inside the horn of the antenna, and there was, let's say, a fair amount of pigeon mess coating the interior surface. They carefully cleaned it all out. They even, and this is a detail I love, they trapped the pigeons, drove them to a site far away, and released them. The pigeons flew right back. Homing instinct. Eventually, the pigeons had to be dealt with more permanently, which Penzias later described with some regret. But the point is, even after cleaning the antenna, even after accounting for every possible terrestrial source of noise, the signal was still there. This mysterious, uniform, low-level microwave hum coming from every direction in the sky equally. And they were stuck. They had this beautiful, unexplained result, and they didn't know what it meant. Meanwhile, just 40 miles away at Princeton University, a physicist named Robert Dicke was leading a team that was actively searching for exactly the signal Penzias and Wilson had found. Dicke and his colleagues, Jim Peebles, Peter Roll, and David Wilkinson, had independently worked out the theoretical prediction that if the universe really did begin in an incredibly hot, dense state, then the radiation from that early fireball should still be detectable today, stretched out by the expansion of the universe from its original ultra-high-energy form into low-energy microwaves. They were actually building their own antenna to look for it. They hadn't found it yet. And then one day, Dicke got a phone call from Penzias, who had heard through a mutual contact that the Princeton group might be able to explain their mysterious noise. The story goes that Dicke hung up the phone, turned to his colleagues and said, "Well, boys, we've been scooped." And that's exactly what had happened. Penzias and Wilson had accidentally discovered the cosmic microwave background, the afterglow of the Big Bang itself. The two groups published companion papers in the Astrophysical Journal in 1965. Penzias and Wilson's paper was remarkably understated. It basically just described the measurement and noted that they had found an excess antenna temperature they couldn't account for. The Princeton paper, published alongside it, provided the theoretical interpretation. This was the remnant radiation from the hot, early universe. Penzias and Wilson would go on to win the Nobel Prize in Physics in 1978 for their discovery. Dicke's team, who had predicted it and knew what it meant, did not share in the prize, which is one of those things that still generates some discussion among physicists. But let's slow down here, because I want you to really understand what the cosmic microwave background is and why it matters so much. Think of it this way. Imagine you're standing far away from an enormous bonfire. The fire was lit a long time ago, and it's been dying down ever since. You can't see the flames anymore, but you can still feel a faint warmth on your skin, coming from every direction because the fire was so vast it surrounded you completely. That residual warmth is something like the cosmic microwave background. In the very early universe, and we're talking about the first few 100,000 years, which sounds like a long time, but is nothing on cosmic scales. The universe was so hot and so dense that it was essentially opaque. It was a seething plasma of particles and radiation, all tangled up together. Photons, which are particles of light, couldn't travel any meaningful distance without slamming into a charged particle and getting scattered in a random direction. The universe was like a thick fog. Light couldn't get through. But as the universe expanded, it cooled. And about 380,000 years after the Big Bang, and that number is worth remembering, 380,000 years, the temperature dropped to roughly 3,000 Kelvin, which is about the surface temperature of a cool red star. At that temperature, something crucial happened. Electrons, which had been flying around freely, finally slowed down enough to be captured by atomic nuclei. Hydrogen atoms formed. Helium atoms formed. This process has a beautiful name, recombination, although that's slightly misleading because the electrons and nuclei had never been combined before, so it was really combination for the first time. But the name stuck. And here's what's really important about recombination. Once the electrons were bound up inside atoms, the universe suddenly became transparent. Photons could finally travel freely through space without constantly being scattered. It's like the fog lifted, and all those photons that were released at that moment, that last scattering surface, as physicists call it, have been traveling through space ever since. For 13.8 billion years, they've been stretched by the expansion of the universe, their wavelengths elongated from the visible and infrared range all the way into the microwave part of the spectrum. And that's what Penzias and Wilson detected, those photons, ancient light released when the universe was 380,000 years old, arriving at a horn antenna in New Jersey after a journey of 13.8 billion years and being mistaken for pigeon interference. Think about what that means. When we detect the cosmic microwave background, we are literally seeing the oldest light in the universe. We're looking at a snapshot of the cosmos when it was less than 0.003% of its current age. It's the baby picture of the universe, and it's coming at us from every direction because that primordial fireball was everywhere. It was the entire universe. Now, the discovery of the CMB, as we usually abbreviate it, was devastating for Hoyle's steady-state theory. Remember, the steady-state model said the universe had no beginning and no end, that it had always looked more or less the same. There was no hot, dense early phase, no primordial fireball, and therefore, no reason to expect a uniform background of microwave radiation filling all of space. Hoyle and his colleagues tried to find alternative explanations. Maybe the microwaves were produced by dust or by some other process. But none of those explanations could account for the extraordinary uniformity and the precise spectrum of the radiation. The CMB looked exactly like what you'd expect from a cooling fireball, and it looked nothing like what any other known process would produce. By the late 1960s, the scientific consensus had shifted decisively in favor of the Big Bang model. Hoyle never fully accepted it. He continued to develop alternative cosmologies until his death in 2001. But the community had moved on. And here's a beautiful detail about the CMB that we didn't fully appreciate until much later. When Penzias and Wilson measured it, it appeared almost perfectly uniform, the same temperature in every direction, to a remarkable degree of precision. And at first, that seemed like a nice, clean result. But it also raised a profound puzzle, one that would gnaw at cosmologists for the next 15 years. Because if the CMB is almost perfectly uniform, that means the early universe was almost perfectly smooth. The same temperature, the same density, everywhere. And yet, when you look at the universe today, it's anything but smooth. You've got galaxies and clusters of galaxies, and vast empty voids and filaments of matter stretching across millions of light years. Structure, clumpiness, complexity. So how do you get from an almost perfectly smooth beginning to the beautifully lumpy universe we see today? There had to be tiny imperfections in that early smoothness, tiny variations in density and temperature, that gravity could amplify over billions of years into the structures we see now. Seeds. The universe needed seeds. And finding those seeds, those tiny ripples in the cosmic microwave background, would become one of the great quests of late 20th century cosmology. It would require building instruments of almost absurd sensitivity and launching them into space, far above the interference of Earth's atmosphere. And the person who would lead that effort, who would spend decades of his career chasing variations so small they amounted to 1 part in 100,000 of the background temperature, was a physicist named George Smoot, working out of Lawrence Berkeley National Laboratory in California. And the satellite that would finally capture those ripples in a map that cosmologists sometimes call the most important image ever taken was called COBE, the Cosmic Background Explorer. And COBE is one of those stories where you realize just how much patience and stubbornness goes into doing science at the highest level, because the road from "we need a satellite to measure the CMB" to "we actually have a map of the early universe" was not a short one, not even close. George Smoot first started thinking seriously about measuring these tiny fluctuations in the CMB back in the early 1970s. And at that point, nobody even knew for sure that the fluctuations existed. It was a theoretical expectation. You needed them to explain how structure formed. But the instruments of the day couldn't see them. The variations were just too small. Think about what we're talking about here. The CMB has a temperature of about 2.725 Kelvin. And the ripples Smoot was hunting for were variations of maybe 30 millionths of a degree, 30 microkelvins. That's like trying to measure the height of a bacterium while standing on top of a skyscraper. The signal is real, but it's buried under layers and layers of noise. Noise from the instrument itself, noise from the atmosphere, noise from the Milky Way, noise from everything. So Smoot and his colleagues tried everything they could think of from the ground first. They flew instruments on high-altitude balloons, which got them above most of the atmosphere. They even mounted detectors on U-2 spy planes. Yes, the same U-2 reconnaissance aircraft from the Cold War. Because those planes could fly at 70,000 feet, way above the bulk of atmospheric water vapor that absorbs and emits microwaves and messes up your measurements. And these early experiments were genuinely heroic efforts. Imagine strapping a delicate microwave radiometer into the nose of a plane that was originally designed to photograph Soviet missile sites, and then flying it at the edge of the stratosphere while trying to measure temperature differences smaller than anything anyone had ever measured before. They got some results. They confirmed the overall smoothness of the CMB to better and better precision. but they couldn't find the ripples. The fluctuations were smaller than their instruments could detect. And here's the thing. Every time you fail to find the ripples, the problem actually gets more interesting in a frustrating kind of way. Because each non-detection tells you the fluctuations must be even smaller than you thought, which means the early universe was even smoother than you thought, which makes the puzzle of how you get from smooth to lumpy even harder to explain. By the late 1970s, the upper limits on CMB anisotropy were getting tight enough that some theorists were starting to get nervous. How could the universe be this smooth and still produce galaxies? Now, right around this time, 1979, 1980, a young physicist named Alan Guth at Stanford was working on a completely different problem in particle physics, something related to magnetic monopoles, which are these hypothetical particles that grand unified theories predicted should exist in enormous numbers but that nobody had ever found. And in the process of thinking about that problem, Guth stumbled onto an idea that would transform cosmology. He called it inflation. Let me try to explain what inflation is, because it's one of those concepts that sounds simple on the surface, but gets more profound the longer you sit with it. The basic idea is this. In the very first fraction of a second after the Big Bang, we're talking about a time interval so short it's almost meaningless in human terms, something like 10 to the minus 36 seconds after the beginning, the universe underwent a period of extraordinarily rapid expansion. Not the gradual expansion that Hubble observed, not the steady stretching of space that we've been talking about. Something far more dramatic. During inflation, the universe doubled in size, and then doubled again, and then doubled again, over and over, maybe 60 or 70 times in total, all within a tiny sliver of a second. By the end of this inflationary period, a region of space that had been unimaginably small, smaller than a proton, had been stretched to something macroscopic, maybe the size of a grapefruit or larger. Now, why does this help with anything? Well, think about the smoothness problem. Before inflation, you had a tiny patch of universe that was small enough for everything in it to be in thermal contact, meaning light and heat had had time to travel across it and even everything out, the way a hot cup of coffee eventually reaches room temperature. Everything in that tiny patch was at the same temperature, the same density, because it had had time to equilibrate. Then inflation took that tiny, uniform patch and stretched it to an enormous size. So the uniformity we see in the CMB isn't a coincidence or a mystery. It's because everything we can observe today came from a single, causally connected region that got inflated to cosmic proportions. And here's what's really clever. Inflation also explains where the ripples come from, because during this incredibly rapid expansion, quantum mechanical fluctuations, the tiny, random jitters that are built into the fabric of reality at the smallest scales, got stretched along with everything else. Normally, quantum fluctuations are unimaginably small. They operate at scales far below anything you'd ever notice in everyday life. But inflation took those fluctuations and blew them up to astronomical sizes. It turned quantum noise into cosmic structure. The ripples in the CMB, the seeds that would eventually grow into galaxies and clusters and the entire cosmic web, they started as quantum fluctuations. Let that sink in for a moment. The largest structures in the universe, filaments of galaxies stretching hundreds of millions of light years, began as quantum jitters in the first fraction of a second of existence. That's one of the most stunning connections in all of physics, the very small and the very large, linked by this brief moment of exponential expansion. Guth published his inflationary model in 1981, and it immediately caught the attention of the cosmology community because it solved several problems at once: the smoothness problem, the monopole problem, and something called the flatness problem, which we might come back to later. But the original version of inflation had some technical issues. Guth himself recognized that his model didn't have a graceful way to end the inflationary period. Within a couple of years, André Linde in the Soviet Union, and independently, Andreas Albrecht and Paul Steinhardt at the University of Pennsylvania developed improved versions, sometimes called new inflation or slow roll inflation, that resolved these issues. And these models made specific predictions about what the CMB ripples should look like. They predicted that the fluctuations should be nearly scale invariant, meaning the ripples should have roughly the same amplitude at all sizes. They predicted a specific statistical pattern, and they predicted a specific amplitude, roughly 1 part in 100,000. So now you've got a theoretical framework that tells you exactly what to look for. And you've got George Smoot and a growing community of experimentalists who have been trying to find these ripples for over a decade. What they needed was a purpose-built satellite above the atmosphere, with instruments sensitive enough to see those 30 microkelvin variations against a 2.725 Kelvin background. COBE was proposed to NASA in 1974, which gives you a sense of the timeline here. It took until 1989, 15 years, for the satellite to actually launch. 15 years of design, redesign, funding battles, technical challenges, and one devastating setback: the Challenger disaster in 1986. COBE had originally been designed to launch on the space shuttle, and when Challenger exploded, the entire shuttle manifest was thrown into chaos. The COBE team had to completely redesign the satellite to fit on a Delta rocket instead, which was smaller, which meant the whole thing had to be made more compact. They did it in about 2 years, which by space mission standards is almost recklessly fast. And on November 18, 1989, COBE launched from Vandenberg Air Force Base in California, carrying 3 instruments into a polar orbit 600 miles above the Earth. The instrument that mattered most for the ripple hunt was called the DMR, the Differential Microwave Radiometer. And what it did was compare the temperature of the CMB in 2 different directions simultaneously, looking for tiny differences. It scanned the entire sky over the course of a year, building up a map pixel by pixel. And in 1992, George Smoot stood up at a meeting of the American Physical Society and showed the world what COBE had found. The map. Tiny splotches of color, blue for slightly cooler regions, pink for slightly warmer, spread across an oval projection of the entire sky. The fluctuations were there, right where inflation predicted they'd be, right at the amplitude that was expected, about 1 part in 100,000, 30 microkelvins. After 2 decades of searching, the seeds of cosmic structure had been found. The reaction was extraordinary. Stephen Hawking called it the most important discovery of the century, if not of all time. That might have been a bit of hyperbole, but the excitement was real and justified. Because this wasn't just a confirmation of one theory, it was the moment when cosmology became a precision science. Before COBE, cosmology had sometimes been jokingly called the search for 2 numbers, the expansion rate and the deceleration rate. After COBE, it became clear that the CMB contained an almost unimaginable wealth of information about the early universe, encoded in the precise pattern of those tiny temperature variations. You just needed better instruments to read it. Smoot shared the 2006 Nobel Prize in Physics with John Mather, who led another of COBE's instruments, the FIRAS instrument, which measured the overall spectrum of the CMB. and confirmed that it was an almost perfect blackbody, the most perfect blackbody ever observed in nature. That result, by the way, is worth pausing on for a moment. A blackbody spectrum is the kind of radiation emitted by an object in perfect thermal equilibrium. It's a very specific curve, and the CMB matched it to an astonishing degree. When Mather showed the fire-ass spectrum at a conference in 1990, the data points fell so precisely on the theoretical blackbody curve that the audience burst into spontaneous applause. You couldn't even see the error bars because they were smaller than the thickness of the line on the graph. But COBE, as groundbreaking as it was, had relatively coarse resolution. Its map of the CMB was blurry. It could see the large-scale ripples, but not the fine detail. It was like looking at the early universe through frosted glass, and cosmologists knew that the fine detail was where the really juicy information lived. Because the pattern of hot and cold spots in the CMB isn't random. It has a specific statistical structure, a specific pattern of sizes and amplitudes that depends on the fundamental properties of the universe, the density of matter, the density of dark matter, the density of dark energy, the geometry of space, the age of the universe. All of these leave their fingerprints in the precise pattern of CMB fluctuations. To read those fingerprints, you needed a sharper map. And so, even before COBE's results were fully published, the next generation of CMB experiments was already being planned. Ground-based telescopes at the South Pole and in the Atacama Desert of Chile, balloon-borne experiments like Boomerang and Maxima, and most ambitiously, a new satellite, one with 35 times the angular resolution of COBE and far greater sensitivity. NASA called it MAP, the Microwave Anisotropy Probe, and it launched in June of 2001 from Cape Canaveral. After the death of David Wilkinson, one of the Princeton physicists from Dickey's original group, the one who had spent his entire career studying the CMB. The satellite was renamed WMAP in his honor. And what WMAP revealed when its first results came in February of 2003, was nothing short of a baby picture of the universe in stunning clarity. Imagine going from a blurry ultrasound where you could barely make out the shape of a head to a high-definition photograph where you could count individual eyelashes. That's the kind of leap WMAP represented. And the picture it painted was strange, beautiful, and in many ways deeply unsettling, because it confirmed something cosmologists had been suspecting for a few years, but still found hard to swallow. It confirmed that most of the universe is made of stuff we don't understand. But let's not rush to that. Let's sit with what WMAP actually measured, because the way cosmologists extract information from the CMB is one of the cleverest bits of scientific reasoning you'll ever encounter, and it's worth understanding at least the basic idea. So here's what you're working with. You've got this map of the entire sky, and every point on that map has a temperature, the temperature of the microwave background radiation coming from that direction. The average temperature is about 2.725 Kelvin everywhere. But layered on top of that average are tiny fluctuations, hot spots and cold spots, differing from the mean by maybe a few tens of millionths of a degree. Those fluctuations form a pattern, not a regular, repeating pattern like wallpaper, but a statistical pattern, meaning if you analyze the sizes of the spots, some sizes are more common than others. There's a characteristic scale, a preferred spot size, and that tells you something profound. Think of it like listening to a musical chord. If someone plays a chord on a piano, the sound that reaches your ear is a complex wave. It's not a single pure tone, it's a combination of frequencies. But if you run that sound through a spectrum analyzer, You can decompose it into its component frequencies and see which notes are loudest. The CMB works the same way. The pattern of spots on the sky can be decomposed into different angular scales: big spots, medium spots, small spots, and you can measure how much power, how much variation exists at each scale. When you plot that out, power on the vertical axis, angular scale on the horizontal, you get what's called the angular power spectrum of the CMB. And this is where the magic happens. Because the angular power spectrum has peaks, not just one peak, a whole series of them, like harmonics in music. And the positions and heights of those peaks are determined by the physical conditions of the universe at the moment of recombination, 380,000 years after the Big Bang. Each peak encodes different information. The position of the first peak tells you about the geometry of space, whether the universe is flat, positively curved like a sphere, or negatively curved like a saddle. The relative heights of the first and second peaks tell you about the density of ordinary matter, the stuff made of protons and neutrons, what physicists call baryonic matter. The third peak and beyond start telling you about dark matter. The overall shape of the spectrum constrains the Hubble constant, the age of the universe, and a bunch of other parameters. So when WMAP's first-year data came in and the team, led by Charles Bennett at NASA's Goddard Space Flight Center, along with a large collaboration, published their results in February 2003, they could measure these peaks with unprecedented precision. And here's what fell out. First, the geometry. The position of the first peak landed almost exactly where it would need to be if the universe is spatially flat, not curved in either direction, flat. Euclidean geometry, at least on the largest scales. Parallel lines stay parallel forever. The angles of a triangle add up to 180 degrees. Now this might sound unremarkable. You might think, well, of course space is flat. That's just normal. But here's the thing. There's no reason, a priori, why the universe should be flat. General relativity allows for all sorts of curved geometries, and most of them are not flat. For the universe to be flat, the total energy density has to be at a very specific critical value. Too much, and space curves one way. Too little, and it curves the other. The fact that it's flat, or incredibly close to flat, is itself a puzzle, and it's actually one of the things inflation was designed to explain. Inflation takes whatever curvature the universe started with and stretches it out so dramatically that any curvature becomes undetectable, the same way the surface of a balloon looks flat if you inflate it to the size of the Earth. So WMAP's confirmation of flatness was also a confirmation of one of inflation's key predictions. That felt good. But the second result was the strange one. When you added up all the ordinary matter in the universe, all the protons, neutrons, electrons, all the atoms that make up stars and planets and gas clouds and you and me, it came to only about 4.5% of the total energy density needed to make the universe flat. 4.5%. That's it. Everything you've ever seen, everything you've ever touched, every star in every galaxy, it's a rounding error in the cosmic budget. Now, cosmologists already knew about dark matter. The idea had been around since the 1930s, when Fritz Zwicky, a brilliant, cantankerous Swiss-American astronomer at Caltech, noticed that galaxies in the Coma cluster were moving way too fast. He calculated the mass of the cluster based on its visible light, then calculated how much mass you'd need to keep those galaxies gravitationally bound at their observed speeds, and the numbers didn't match. Not even close. The cluster needed something like 400 times more mass than he could see. He called it Dunkle Materie, dark matter. And people mostly ignored him for decades, partly because Zwicky had a personality that made collaboration difficult, to put it gently. He once called his colleagues at Mount Wilson Observatory spherical bastards, because, he said, they were bastards no matter which way you looked at them. But the evidence kept piling up. In the 1970s, Vera Rubin and Kent Ford measured the rotation curves of spiral galaxies and found the same discrepancy. Stars at the edges of galaxies were orbiting just as fast as stars near the center, which made no sense if the only mass present was what you could see. The galaxies should have been flying apart, unless there was a massive halo of invisible matter surrounding each galaxy, providing the extra gravitational pull. Rubin's work, patient and meticulous, and initially met with skepticism, partly because she was a woman in a field that didn't take women seriously, became one of the most compelling pieces of evidence for dark matter. And by the time WMAP flew, the existence of dark matter was well established. It interacts gravitationally, but doesn't emit, absorb, or reflect light. We still don't know what it's made of. That's one of the biggest open questions in physics. But we know it's there, and WMAP measured its contribution at roughly 23% of the total energy density. So you've got 4.5% ordinary matter, 23% dark matter. That's about 27.5% total. But the universe is flat, which means the total has to be 100%. So where's the other 72.5%? And this is where the story takes its wildest turn, because that missing 72.5% WMAP confirmed is something called dark energy. And dark energy is, without exaggeration, one of the most baffling discoveries in the history of science. Here's the backstory. In 1998, just a few years before WMAP launched, two competing teams of astronomers, the Supernova Cosmology Project, led by Saul Perlmutter at Berkeley, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, were both trying to measure the deceleration of the universe's expansion. Because here's what everyone expected. The universe is expanding. We know that from Hubble. But gravity is pulling everything back together. So the expansion should be slowing down over time, the same way a ball thrown upward slows down as Earth's gravity pulls it back. The question was just how much it was decelerating, and the answer would tell you the ultimate fate of the universe, whether it would expand forever, coast to a stop, or eventually collapse back on itself in a big crunch. To measure this, both teams used a particular type of supernova called a Type 1a supernova. These are phenomenally useful because they all explode with roughly the same intrinsic brightness. They're what astronomers call standard candles. If you know how bright something truly is, and you measure how bright it appears from Earth, you can calculate how far away it is. And if you also measure the redshift of the host galaxy, you know how fast it's receding. Do this for supernovae at a range of distances, and you can map out the expansion history of the universe. You can see whether the expansion was faster in the past and is slowing down, or whether something else is going on. Both teams expected to find deceleration. What they found was the opposite. The distant supernovae were dimmer than they should have been, meaning they were farther away than expected. The expansion of the universe wasn't slowing down. It was speeding up. The universe is accelerating. Think about what that means. It's as if you threw that ball into the air, and instead of slowing down and falling back, it started going faster and faster, accelerating away from you into the sky. Something is pushing it. Something is counteracting gravity on the largest scales and winning. That something got the name dark energy. And when Perlmutter, Schmidt, and Rees shared the 2011 Nobel Prize in Physics for this discovery, the Nobel Committee called it the most astounding discovery that the expansion of the universe is accelerating. And here's the kicker. Remember Einstein's cosmological constant? The one he introduced in 1917 to keep the universe static, and then supposedly called his greatest blunder after Hubble showed the universe was expanding? It turns out that a cosmological constant, a constant energy density permeating all of space, is the simplest mathematical description of dark energy. Einstein's blunder might have been right all along, just for the wrong reasons. He added it to prevent expansion. In reality, it drives accelerated expansion. The mathematical form is the same. The universe, it seems, has a sense of irony. WMAP's data, combined with the supernova results and other measurements, painted a remarkably precise and remarkably strange picture. The universe is 13.7 billion years old, later refined to 13.8 billion by WMAP's successor. It's geometrically flat. It's made of roughly 4.5% ordinary matter, 23% dark matter, and 72.5% dark energy. We understand the 4.5% reasonably well. The rest, 95.5% of everything that exists, we can describe mathematically, but don't truly understand. And that's the state of affairs as of 2003. The concordance cosmology, sometimes called the lambda CDM model. Lambda for the cosmological constant representing dark energy, CDM for cold dark matter. It fits the data beautifully. The CMB power spectrum, the supernova measurements, the large-scale distribution of galaxies, the abundance of light elements from Big Bang nucleosynthesis, all of it clicks together into a single coherent picture. It's one of the great triumphs of modern science, this convergence of completely independent lines of evidence pointing to the same weird conclusion. But WMAP wasn't the end of the CMB story. Even as its data was being analyzed and published, 9 years of observations in total, with increasingly refined data releases, the European Space Agency was building something even more ambitious, a satellite called Planck, named after Max Planck, the father of quantum theory. And Planck would push the precision of CMB measurements to their theoretical limits, squeezing out every last drop of information that the cosmic microwave background had to offer. It launched in May of 2009 from French Guiana, and it carried instruments cooled to 1/10 of a degree above absolute zero, colder than anything in nature, colder than the CMB itself, because to measure microwaves that faint, your detector has to be quieter than the thing it's trying to hear. That's the whole game with these instruments. If your detector is warm, it's radiating its own microwaves, and those swamp the signal you're looking for. It's like trying to listen for a whisper in a room full of people talking. You have to make the room silent first. And Planck's room was extraordinarily silent. 1/10 of a Kelvin, achieved through a cascade of cooling stages, each one chilling the instruments further, the final stage using a dilution refrigerator that mixed 2 isotopes of helium to reach temperatures that, honestly, almost defy intuition. 1/10 of a degree above the coldest anything can possibly be. And at that temperature, Planck's detectors could pick up variations in the CMB with a sensitivity and angular resolution that made WMAP look like a rough sketch. Now, WMAP was brilliant. Let's be clear about that. It gave us the concordance model, it confirmed flatness, it measured the age of the universe. But WMAP's angular resolution was about 13 arc minutes. That's roughly 1/3 of the apparent diameter of the full moon. Planck could resolve features down to about 5 arc minutes. That might not sound like a dramatic improvement, but in cosmology, going from 13 to 5 arc minutes is enormous. It means you can see finer details in the CMB temperature map, which means you can measure more peaks in the power spectrum, which means you can pin down the cosmological parameters with much tighter error bars. And tighter error bars matter, because when you're trying to distinguish between competing theories of the early universe, the difference often lives in the fourth decimal place. Planck also observed in 9 frequency bands compared to WMAP's 5. More frequency bands means better ability to separate the actual CMB signal from foreground contamination, all the stuff between us and the surface of last scattering that also emits microwaves. Dust in our own galaxy, synchrotron radiation from charged particles spiraling in magnetic fields, free emission from hot gas. All of that has to be carefully modeled and subtracted to get at the primordial signal underneath. With 9 bands, Planck could do that subtraction with much greater confidence. The first major Planck results came out in March of 2013, and they were stunning. The map itself, if you've ever seen it, that oval projection of the whole sky in blue and red splotches, was the most detailed portrait of the infant universe ever made. And the power spectrum derived from that map was exquisite. Smooth, precise, with peaks and troughs measured to extraordinary accuracy. The basic picture confirmed what WMAP had found, but sharpened everything. The age of the universe, 13.798 billion years, plus or minus about 37 million. The Hubble constant, the current expansion rate, measured at about 67.3 kilometers per second per megaparsec. Ordinary matter, 4.9%. Dark matter, 26.8%. Dark energy, 68.3%. These numbers shifted slightly from WMAP's values, but the overall framework held. Lambda CDM was still king. Here's what's really interesting, though. One of those numbers, the Hubble constant, would become the center of a genuine scientific controversy that's still unresolved as of now, and it's worth spending some time on, because it tells you something important about how science works when the data doesn't cooperate. So Planck measured the Hubble constant at about 67.3 kilometers per second per megaparsec. That means for every megaparsec of distance, about 3.26 million light-years, galaxies are moving away from us 67.3 kilometers per second faster. But here's the thing. There's another way to measure the Hubble constant that doesn't involve the CMB at all. You can do it the old-fashioned way, the way Hubble himself pioneered, by looking at objects in the relatively nearby universe and directly measuring their distances and recession velocities. And the modern version of this approach, led most prominently by Adam Rees, the same Adam Rees who co-discovered the accelerating expansion, uses a refined distance ladder, Cepheid variable stars to calibrate distances to nearby galaxies, then Type 1a supernovae in those same galaxies to extend the ladder further out. It's painstaking work, and Rees and his team have been refining it for years. Their measurement? About 73 kilometers per second per megaparsec. Not 67, 73. Now, you might think, okay, 67 versus 73, that's pretty close, right? In everyday life, sure. But in precision cosmology, these measurements come with small error bars. Planck's error bars don't overlap with Rees's error bars. The discrepancy is statistically significant, somewhere around 4 to 5 sigma, depending on exactly which datasets you compare. In physics, 5 sigma is traditionally the threshold for claiming a discovery. So this isn't a minor quibble. This is a genuine tension in the data. And it's been called the Hubble tension. Think about what it means. two completely independent ways of measuring the same number, the current expansion rate of the universe. And they disagree. One method looks at the very early universe, the CMB, and uses the lambda CDM model to extrapolate forward to today. The other looks at the relatively nearby universe and measures expansion directly. They should give the same answer. They don't. So either one of the measurements is wrong, there's some systematic error that hasn't been identified, or the lambda CDM model is missing something. Maybe the universe's expansion history is more complicated than a simple cosmological constant would predict. Maybe dark energy isn't constant. Maybe there's some new physics in the early universe, some extra species of neutrino or some exotic form of radiation that changes how the CMB power spectrum maps onto the expansion rate. People have proposed all sorts of ideas. As of now, none of them have gained consensus. The tension persists, and it's one of the most actively debated questions in all of cosmology. But let's come back to that, because there's more to the Planck story that deserves attention. Beyond the basic parameters, Planck tested inflation with unprecedented precision. Remember, inflation predicts that the tiny quantum fluctuations blown up to cosmic scales should have a particular statistical character. They should be nearly scale invariant, meaning roughly the same amplitude at all sizes, but with a slight tilt. The power spectrum should be just slightly stronger at large scales than at small scales. This tilt is quantified by a number called the spectral index, usually written as n sub s. Perfect scale invariance would be n sub s equals exactly 1. Inflation predicts it should be slightly less than 1, something like 0.96 or 0.97. Planck measured it at 0.9603, plus or minus 0.0073. Less than 1, just as inflation predicted. That's a beautiful confirmation. It means the fluctuations really do have the character you'd expect if they were generated by a quantum field during an inflationary epoch. Not a proof of inflation. It's very hard to prove something that happened in the first trillionth of a trillionth of a trillionth of a second, but a strong piece of supporting evidence. There's another prediction of inflation that Planck went hunting for, and this one is more subtle. During inflation, the rapid expansion should have generated not just density fluctuations, the seeds of galaxies, but also gravitational waves, ripples in space-time itself, stretched to enormous scales. These primordial gravitational waves would leave a distinctive imprint on the CMB, not in the temperature pattern, but in the polarization pattern. Specifically, they'd create a type of polarization called B-mode polarization, a kind of swirling pattern that density fluctuations alone can't produce. Finding B-modes from inflation would be a smoking gun. It would tell us the energy scale at which inflation happened, which would be an extraordinary piece of information about physics at energies far beyond anything we can reach with particle accelerators. And in March of 2014, almost exactly a year after Planck's first results, a team using a ground-based telescope at the South Pole called BICEP-2 announced that they had detected B-mode polarization. The signal was strong, much stronger than many theorists had expected. The press conference was dramatic. The lead scientist, John Kovacs, presented the results, and the physics world erupted with excitement. Some people called it the discovery of the century. If confirmed, it would have been direct evidence of quantum gravity, of inflation, of physics at unimaginable energies. But here's the thing. Within weeks, doubts began to surface. The BICEP-2 team had observed at a single frequency, 150 gigahertz, and at that frequency, there's a potential contaminant, dust in our own galaxy. tiny grains of interstellar dust, elongated and aligned by the galaxy's magnetic field, emit polarized microwave radiation. And that polarized dust emission can mimic the B-mode signal from primordial gravitational waves. The BICEP 2 team had tried to account for galactic dust, but they'd relied on preliminary, incomplete dust models. When the Planck team released their own dust polarization maps later in 2014, it became clear that the dust contamination in the region of sky BICEP 2 had observed was significantly higher than the BICEP 2 team had assumed. A joint analysis by the BICEP 2 and Planck teams, published in early 2015, concluded that the signal was consistent with being entirely due to dust. The claimed detection evaporated. It was a painful episode, not because anyone had done anything wrong exactly, but because the excitement had gotten ahead of the evidence. The BICEP 2 scientists were careful researchers who made a judgment call about dust modeling that turned out to be incorrect, and the broader community, hungry for a breakthrough, had amplified the announcement before the cross-checks were complete. It's worth sitting with that story for a moment, because it illustrates something important about how science really works. The narrative we usually hear is discovery, confirmation, Nobel Prize, but the reality is messier. Sometimes you think you've found something extraordinary, and it turns out to be dust, literally dust. And the way you find out is by having independent teams with different instruments check each other's work. That's not a failure of the process. That is the process. Planck checking BICEP 2 is exactly how science is supposed to function, and the search for primordial B-modes continues. Newer experiments, BICEP 3, the BICEP array, the Simons Observatory being built in Chile's Atacama Desert, and eventually a proposed satellite mission called Lightbird from the Japanese Space Agency, are all designed to push the sensitivity further, to either detect those gravitational waves at a lower amplitude than BICEP 2 claimed, or to place increasingly tight upper limits that constrain which models of inflation are viable. Because even a non-detection tells you something. If the gravitational wave signal is very small, that rules out certain classes of inflationary models and favors others. The absence of evidence in this case really is evidence of absence, or at least evidence that the energy scale of inflation is lower than some theories predict. So by the mid-2000s, the picture of the universe that emerges from the CMB is extraordinarily detailed and, in most respects, extraordinarily consistent. Lambda CDM works. Inflation works, at least in its broad predictions. The universe is flat. It's 13.8 billion years old. It's made of roughly 5% atoms, 27% dark matter, and 68% dark energy. The fluctuations in the CMB match what inflation predicts. The peaks in the power spectrum encode the physics of the early universe with remarkable fidelity. But there are these cracks. The Hubble tension. The fact that we don't know what dark matter is. The fact that we don't know what dark energy is. The fact that inflation, for all its predictive success, doesn't have a single agreed-upon mechanism. There are hundreds of inflationary models, and while Planck has ruled out some of them, many remain viable. And lurking beneath all of this is a deeper question, one that takes us back before inflation, before the hot dense state, before the CMB, before nucleosynthesis, back to the very beginning, or rather, to the question of whether there even was a very beginning. Because when you rewind the expansion of the universe all the way back, when you follow it to its logical conclusion, you arrive at a point where the density and temperature become infinite, where the equations of general relativity break down, where space-time itself ceases to make sense. And that's where we are now. right at the edge of what physics can actually describe. Think about what that means. General relativity, Einstein's masterpiece, the theory that predicted the expansion of the universe, that explained the bending of starlight around the sun, that gave us black holes and gravitational waves and the entire framework for modern cosmology. That theory, when you push it all the way back to time zero, basically throws up its hands. It produces infinities. And in physics, when your equations give you infinity, that's not an answer. That's a cry for help. It means your theory has reached its limit. It means something is missing. The technical term for this is a singularity, and you've probably heard that word before, maybe in the context of black holes, because it's the same kind of problem. At the center of a black hole, general relativity predicts that matter gets crushed to a point of infinite density. At the beginning of the universe, the same thing happens. Everything compressed into a state of infinite density and infinite temperature. The math just breaks. And here's the thing that's really important to understand. The singularity isn't a place. It's not a tiny dot sitting in space. It's not an object. It's the breakdown of the theory itself. It's general relativity telling you, I cannot describe this. You need something else. So what's the something else? Well, this is where we get into one of the deepest unsolved problems in all of physics. And I mean genuinely unsolved. Not one of those problems where scientists kind of know the answer, but haven't quite nailed down the details. This is a problem where the broad outlines of the solution are still being debated, where there are competing frameworks, where brilliant people have spent entire careers working on it, and we still don't have a definitive answer. The problem is this: how do you reconcile general relativity with quantum mechanics? Let's talk about why that's so hard, because on the surface you might think, well, we have a theory of gravity, general relativity, and we have a theory of everything else, quantum mechanics and its extensions into quantum field theory. Both work spectacularly well. General relativity describes the large-scale structure of the universe, the behavior of space-time, the motion of planets and galaxies. Quantum mechanics describes the small-scale world, atoms and particles and forces. In everyday physics, these two theories almost never overlap. Gravity is so weak at the scale of individual particles that you can just ignore it. And quantum effects are so tiny at the scale of planets and stars that you can ignore them too. The two theories live in separate houses, and they don't bother each other. But there are situations, rare, extreme situations, where both theories matter at the same time, where you have something that is simultaneously very massive and very small. And the most obvious example is the beginning of the universe. When the entire observable universe is compressed into a region smaller than an atom, you can't ignore gravity because the density is unimaginable, and you can't ignore quantum mechanics because the scale is subatomic. You need both. You need a theory of quantum gravity, and we don't have one, not a complete, tested, confirmed one. Now, it's not for lack of trying. People have been working on this since at least the 1930s, when physicists first started noticing that the straightforward methods you use to make other forces quantum mechanical, a process called quantization, don't work for gravity. When you try to apply the standard techniques of quantum field theory to general relativity, you get infinities everywhere, and not the kind of infinities you can sweep under the rug with the mathematical tricks that work for electromagnetism and the nuclear forces. Gravity, quantized naively, is what physicists call non-renormalizable. The infinities just keep multiplying, and you can't extract sensible predictions. So people got creative. And the two most prominent approaches that emerged over the decades are string theory and loop quantum gravity. Let me walk you through each, gently, because even the basic ideas are fascinating. String theory, and this is a story that really gets going in the late 1960s and 1970s, starts with a radical idea. What if the fundamental building blocks of nature aren't point-like particles? What if, instead, they're tiny, one-dimensional vibrating strings? Unimaginably small, on the order of the Planck length. That's about 10 to the minus 35 meters. So small that if an atom were blown up to the size of the observable universe, a string would still be smaller than a tree. These strings vibrate at different frequencies, and each mode of vibration corresponds to a different particle. One vibration pattern gives you a photon, another gives you an electron, another gives you a quark. And here's what's really beautiful. One of the vibration modes naturally produces a massless spin 2 particle, which is exactly what a graviton, the hypothetical quantum carrier of gravity, would be. String theory doesn't just accommodate gravity, it demands it. Gravity falls out of the math automatically. That's what got people so excited in the 1980s and 1990s. Figures like John Schwartz and Michael Green showed in 1984 that certain versions of string theory were mathematically consistent in ways that nobody expected. A result so surprising it kicked off what's called the first superstring revolution. Edward Witten, widely regarded as one of the most brilliant mathematical physicists alive, helped unify 5 different versions of string theory into a single overarching framework called M-theory in 1995. The intellectual energy around string theory was enormous. It felt, to many physicists, like the answer was just around the corner. But here's the catch, and it's a big one. String theory requires extra dimensions of space. Not 3, but 9 spatial dimensions, or 10 in M-theory. The extra dimensions are supposed to be curled up so small that we can't detect them, compactified into tiny geometric shapes. And the way those extra dimensions are curled up determines what kind of physics you get in the 3 large dimensions we experience. The problem is that there are an astronomical number of ways to curl them up. Estimates range from 10 to the 500 different possibilities, a number so large it's essentially meaningless. Each configuration gives you a different version of physics, with different particle masses, different force strengths, different constants. And we don't have a way to determine which configuration corresponds to our universe. This is the landscape problem, and it's been one of the most contentious issues in theoretical physics for the last 2 decades. Critics argue that a theory that can predict essentially anything predicts nothing. Supporters argue that the framework is still being developed, that the mathematical richness is a feature, not a bug, and that the landscape might be navigated by other principles we haven't discovered yet. And then there's the other major approach, loop quantum gravity, which takes a completely different philosophy. Instead of adding new ingredients like strings and extra dimensions, loop quantum gravity tries to quantize general relativity directly, taking seriously the idea that space-time itself is the thing that needs to be made quantum mechanical. The key figures here include Abhay Ashtekar, who in 1986 reformulated general relativity in a way that made it more amenable to quantization, and Lee Smolin and Carlo Rovelli, who in the early 1990s developed the loop representation that gives the theory its name. The basic picture that emerges is striking. In loop quantum gravity, space is not smooth and continuous at the smallest scales. Instead, it has a granular structure, like a fabric woven from tiny discrete loops. Volume comes in minimum chunks. Area comes in minimum chunks. You can't have a piece of space smaller than a certain size, just like you can't have less than 1 quantum of energy in a photon. Space-time, in this picture, is literally made of atoms. Atoms of geometry, not atoms of matter. The technical structure involves something called spin networks, which are graph-like structures where the nodes and edges carry quantum numbers that encode the geometry of space. And here's what's particularly relevant for our story about the Big Bang. In loop quantum gravity, the singularity might not exist. Because space has a minimum size, you can't compress everything to a point of infinite density. The granular structure of space-time acts like a floor. It prevents the collapse from going all the way to zero. And what some calculations suggest, pioneered by Martin Bojewald in the early 2000s, is that instead of a singularity, you get a bounce. The universe, in this picture, was contracting before the Big Bang, reached a minimum size dictated by quantum geometry, and then bounced outward into the expansion we observe today. The Big Bang wasn't the beginning. It was a transition. A big bounce. Now, I want to be really careful here, because this is speculative. Loop quantum cosmology is a simplified application of a theory that itself isn't complete. The calculations involve significant approximations, and not everyone in the field agrees that the bounce result is robust. But the idea is genuinely fascinating, and it illustrates something important. When you try to apply quantum gravity to the very beginning of the universe, the classical singularity, that point of infinite density where everything breaks down, might simply go away. It might be an artifact of using the wrong theory, like trying to describe ice by using equations that only apply to liquid water. The equations aren't wrong, exactly. They're just being applied beyond their domain of validity. And this connects to something even more mind-bending, which is the question of what time itself means at the very beginning. In general relativity, time is part of space-time. It's woven into the fabric of the universe. But if space-time itself breaks down at the singularity, then time breaks down too. Asking what happened before the Big Bang might be like asking what's north of the North Pole, to use Stephen Hawking's famous analogy. The question might not have a meaningful answer, not because the answer is hidden, but because the question itself assumes a framework that doesn't apply. Hawking, working with James Hartle in the early 1980s, proposed something called the no-boundary proposal, which tries to address exactly this. The idea, roughly, is that as you go back toward the beginning of the universe, the dimension of time gradually becomes more and more like a dimension of space. There's no sharp boundary, no edge, no moment of creation. The universe is finite in the past, but has no beginning, in the same way that the surface of a sphere has a finite area, but no edge. It's a beautiful idea, mathematically elegant, but extraordinarily difficult to test. And it's just one of several proposals. Alexander Vilenkin proposed a different picture, tunneling from nothing, where the universe quantum mechanically tunnels into existence from a state of literally nothing. No space, no time, no matter. Roger Penrose has his conformal cyclic cosmology, where the universe goes through infinite cycles, each Big Bang being the continuation of a previous universe that expanded and cooled until all structure was lost. Each of these ideas is trying to answer the same question: what, if anything, came before? And each of them requires a theory of quantum gravity to make fully rigorous, which brings us back to the central problem. Without a complete, testable theory of quantum gravity, we can sketch these pictures, we can explore their mathematical consequences, but we can't definitively say which one, if any, is correct. And yet, and this is what I find so remarkable, we're not completely in the dark, Because even though we can't probe the Planck epoch directly, the signatures of whatever happened at the very beginning might be imprinted on things we can observe. The spectrum of primordial fluctuations, the polarization of the CMB, the distribution of galaxies on the largest scales. These are all downstream consequences of the physics of the earliest moments. Different models of quantum gravity, different pre-Big Bang scenarios, make subtly different predictions about these observables. And as our instruments get better, as we map the CMB with greater precision, as we build gravitational wave detectors sensitive to lower and lower frequencies, we might start to distinguish between them. In fact, there's a whole class of experiments being planned or already underway that could shed light on this. Gravitational wave observatories like LISA, the Laser Interferometer Space Antenna, a joint ESA-NASA mission planned for the 2030s, will be sensitive to gravitational waves from the very early universe, potentially from phase transitions or even from the end of inflation itself. And the patterns in those waves could carry information about physics at energy scales we can never reach with particle accelerators. Think about that. We might be able to test theories of quantum gravity, not by smashing particles together, but by listening to the faint gravitational hum left over from the birth of the universe itself. Ripples in space-time, traveling for billions of years, carrying a message from an era we thought we'd never be able to study. That's not science fiction. That's the plan. And LISA isn't the only one. There are pulsar timing arrays, projects like Nanograv, the European Pulsar Timing Array, the Parkes Pulsar Timing Array in Australia, that use millisecond pulsars, these incredibly precise natural clocks scattered across our galaxy, to detect gravitational waves at even lower frequencies than LISA will target. In 2023, Nanograv actually announced strong evidence for a gravitational wave background, a kind of constant hum of gravitational waves permeating all of space. Now, the leading explanation for that signal is merging supermassive black holes, pairs of enormous black holes spiraling together in the centers of distant galaxies. But here's what's tantalizing. Some of that signal could, in principle, have contributions from the very early universe. From cosmic strings, maybe, if they exist. These are hypothetical one-dimensional defects in space-time that some models of the early universe predict should have formed during phase transitions as the universe cooled, or from other exotic processes tied to inflation or to whatever preceded it. Disentangling those contributions is incredibly difficult, but the data is getting better every year. So let's step back for a moment and think about where we actually are in this story, because it's worth appreciating just how much the picture has changed, even in the last couple of decades. When I started talking about this, we were in a world where people weren't even sure the universe had a beginning. Einstein didn't want it to. Hoyle fought against it his whole career. And now, here we are, not just confident that the universe began in an unimaginably hot, dense state, roughly 13.8 billion years ago, but actively designing experiments to probe the first trillionth of a trillionth of a trillionth of a second. The precision of modern cosmology is genuinely staggering. We know the age of the universe to within about 50 million years. We know the relative proportions of ordinary matter, and dark energy to within a percentage point or two. We have a 6-parameter model, lambda CDM, that fits an extraordinary range of observations with remarkable accuracy. And yet, there are cracks. There are things we don't understand. And some of those cracks might be the most interesting part of the whole story. Let's talk about dark matter for a moment, because it's one of those things that sits right at the intersection of what we know and what we don't know. We've mentioned it a few times. It makes up about 27% of the total energy content of the universe, roughly 5 or 6 times as much as ordinary matter. We know it's there because of its gravitational effects. Galaxies rotate too fast for the amount of visible matter they contain. Galaxy clusters are too massive. The way light bends around large structures, gravitational lensing, tells us there's more mass than we can see. And crucially, the pattern of fluctuations in the cosmic microwave background, those tiny temperature variations that COBE first detected and WMAP and Planck mapped in exquisite detail, those patterns only make sense if dark matter exists. The acoustic peaks in the CMB power spectrum, the specific angular scales at which the fluctuations are strongest, are incredibly sensitive to the ratio of ordinary matter to dark matter. If you try to fit the data without dark matter, it just doesn't work. The peaks are in the wrong places, with the wrong heights. So, we're very confident dark matter is real. What we don't know is what it actually is. And that's been one of the great open questions in physics for decades now. The leading candidates for a long time were WIMPs, weakly interacting massive particles. The idea was elegant. If you had a new particle with a mass somewhere in the range of, say, 10 to 1,000 times the mass of a proton, and it interacted via the weak nuclear force, then you could calculate how much of it would be left over from the early universe, and the answer came out almost exactly right. This was called the WIMP miracle, and it motivated an enormous experimental effort. Underground detectors like Xenon, LUX, Pandax, these are experiments buried deep beneath mountains or in old mines, using tanks of ultra-pure liquid xenon, waiting for a dark matter particle to bump into a xenon nucleus and produce a tiny flash of light. Decades of searching, incredible sensitivity. And so far, nothing. No confirmed detection. That doesn't mean WIMPs are ruled out entirely. There's still parameter space to explore. But the simplest versions of the WIMP hypothesis are looking increasingly constrained. And so attention has been broadening to other candidates. Axions, for instance, very light particles originally proposed in the late 1970s to solve a different problem in particle physics, something called the strong CP problem, which is about why the strong nuclear force respects a certain symmetry that it has no obvious reason to respect. It turns out that if axions exist, they could also be produced in enormous quantities in the early universe and could serve as dark matter. Experiments like ADMX, the Axion Dark Matter Experiment, are searching for them using sensitive microwave cavities threaded by strong magnetic fields, looking for the faint signal of an axion converting into a photon. It's painstaking work, scanning through frequencies one narrow band at a time, but the sensitivity keeps improving. And then there are more exotic possibilities. Primordial black holes. Black holes that formed not from collapsing stars, but from density fluctuations in the very early universe, possibly during or just after inflation. If some regions of the infant universe were just slightly denser than their surroundings, they could have collapsed directly into black holes. Depending on when they formed, these primordial black holes could have a wide range of masses, from tiny, smaller than an asteroid, to tens or hundreds of solar masses. And some fraction of dark matter, maybe all of it, could be made of these objects. The gravitational wave detections by LIGO and Virgo of merging black holes with somewhat unexpected masses rekindled interest in this idea, though the current consensus is that primordial black holes probably can't account for all of dark matter. Various observational constraints, from gravitational lensing surveys, from the effects such black holes would have on the CMB, from the survival of certain fragile astrophysical systems, rule out most of the mass range. But not all of it. There are still windows. Here's what I find fascinating about the dark matter problem. It's a reminder that our beautiful, precise cosmological model is, in a very real sense, a model of our ignorance as much as our knowledge. We can describe what dark matter does, how it clumps, how it gravitates, how it shaped the large-scale structure of the universe, with extraordinary accuracy. But we cannot tell you what it is made of. We've never held a piece of it. We've never seen it in a detector. We infer its existence entirely from its gravitational fingerprints. And that's okay. That's how science often works. You see the shadow before you see the thing casting it. But it does mean there's a whole sector of reality, the dominant form of matter in the universe, that remains fundamentally mysterious. Dark energy is even stranger. At least with dark matter, we have a clear physical picture. It's some kind of stuff, some particle or object, that has mass and gravitates. Dark energy is, well, it's the thing that's making the expansion of the universe accelerate. Remember, when we talked about the supernova observations in 1998, the two teams, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees. They found that distant Type 1A supernovae were dimmer than expected, meaning they were farther away than they should have been if the expansion of the universe were slowing down. The expansion wasn't slowing down. It was speeding up. That discovery won the Nobel Prize in 2011, and it forced us to accept that roughly 68% of the energy content of the universe is in this form that acts like a kind of anti-gravity, pushing space apart. The simplest explanation is Einstein's cosmological constant, the thing he introduced back in 1917 to keep the universe static, then supposedly called his greatest blunder, and which turned out to be needed after all, just not for the reason he originally imagined. In the language of modern physics, the cosmological constant is equivalent to the energy of empty space itself, the vacuum energy. And here's where things get deeply uncomfortable, because when you try to calculate the vacuum energy using quantum field theory, you get a number that is roughly 120 orders of magnitude too large. That's not a small discrepancy. That's 10 to the power of 120. It's been called the worst prediction in the history of physics. Something is clearly wrong with our understanding, either of quantum field theory or of gravity, or of how they fit together, and that, once again, points back to the need for a theory of quantum gravity. But maybe the cosmological constant isn't actually constant. Maybe dark energy evolves over time. There are models, quintessence models they're called, where dark energy is a dynamic field that changes as the universe expands. In some of these models, dark energy was negligible in the early universe and only became dominant recently, in cosmological terms. In others, it could change character in the future, potentially even reversing, leading to a scenario where the expansion of the universe eventually slows down again, or even reverses into a contraction, a big crunch. Some models predict a big rip where the acceleration becomes so extreme that it eventually tears apart galaxies, then solar systems, then atoms themselves. The fate of the universe depends quite literally on the nature of dark energy, and we're starting to get data that might help us figure this out. The Dark Energy Spectroscopic Instrument, DESI, began its main survey in 2021 from the Kitt Peak National Observatory in Arizona. It's mapping the three-dimensional positions of tens of millions of galaxies and quasars, building the most detailed map of the large-scale structure of the universe ever made. By measuring how that structure has evolved over the last 11 billion years, DC can trace the expansion history of the universe with unprecedented precision. And in early 2024, the DESI collaboration released its first-year results, and they contained a hint, tentative, preliminary, not yet conclusive, that dark energy might not be constant after all, that its equation of state might be changing with time. If that holds up with more data, it would be enormous. It would mean the cosmological constant isn't the whole story. It would open up entirely new physics. And then there's the Hubble tension, which we talked about earlier. The disagreement between the expansion rate measured from the early universe using the CMB and the rate measured from the local universe using supernovae and Cepheid variables. Planck gives you about 67 kilometers per second per megaparsec. The local measurements, refined over years by Adam Rees and his team, consistently give you about 73. That gap has stubbornly refused to close, and it's now significant enough, 4 to 5 sigma, that most cosmologists take it seriously as a potential sign of new physics rather than just a systematic error. Could it be related to dark energy evolving? Could it be a sign that there's an extra component in the early universe we haven't accounted for? Maybe an extra species of neutrino, or some kind of early dark energy that was present before recombination and then faded away? There are dozens of proposed solutions, and none of them has emerged as the clear winner yet. But every new dataset narrows the possibilities. What strikes me about all of this, the dark matter searches, the dark energy surveys, the Hubble tension, the gravitational wave observatories, is that we're living through a period where cosmology is being transformed from a data-starved field into a data-rich one. For most of human history, we could only look up and wonder. Then we could look through telescopes and catalog. Then we could measure redshifts and map expansion. And now we're at a point where we have multiple independent, high-precision probes of the universe's history, composition, and geometry. And they're starting to tell us things that don't quite fit together. And that's exciting. That's where new physics comes from. Not from everything agreeing perfectly, but from the cracks, the tensions, the places where the model creaks under the weight of better data. There's one more piece of this puzzle that I want to talk about, because it connects everything we've discussed. The beginning of the universe, the nature of space-time, the fate of everything. And it's something that has been quietly revolutionizing the way physicists think about the cosmos for the last couple of decades. And that's the idea of information. What it is, where it lives, and whether the universe, at its most fundamental level, is not made of matter or energy or even space-time, but of something more abstract, something almost mathematical. Now, I know that sounds like it's veering into philosophy, and in some ways it is, but stay with me, because this connects directly to the Big Bang, to black holes, to the reason the universe looks the way it does, and it might be the deepest clue we have about what was really going on at the very beginning. Let's start with a name you've heard before in a very different context: John Archibald Wheeler. He was one of the towering figures of 20th century physics. He worked on the Manhattan Project. He coined the term black hole. He was Richard Feynman's doctoral advisor at Princeton. And late in his career, in the 1980s and 1990s, Wheeler became almost obsessed with a single phrase he invented: it from bit. What he meant was that every physical quantity, every particle, every field, every force, ultimately derives its existence from information. Not information in the colloquial sense, like data on a hard drive, but information in the deepest sense. Binary choices, yes or no answers, the irreducible distinctions that define what something is versus what it isn't. Wheeler believed that when you drill down far enough, the universe isn't made of stuff. It's made of answers to questions. Now, that might sound poetic and vague, and when Wheeler first proposed it, a lot of physicists nodded politely and moved on. But then, something happened that made people take this idea much more seriously, and it came from an unlikely direction, from black holes. You remember we talked about singularities, those points where general relativity breaks down, where density goes to infinity, and the math stops making sense. Black holes have singularities at their centers, and for a long time, the main question about black holes was what happens to stuff that falls in. But in the early 1970s, a young physicist named Jacob Bekenstein, who was a student of Wheeler's, there's that connection again, proposed something radical. He said black holes have entropy. Now, entropy is a measure of disorder, but more precisely, it's a measure of the number of microscopic arrangements that could give rise to the same macroscopic appearance. And Bekenstein argued that the entropy of a black hole is proportional not to its volume, which is what you'd naively expect, but to the area of its event horizon. The surface, not the interior. Stephen Hawking initially resisted this idea, but then in 1974, he showed that black holes actually do radiate. They emit what we now call Hawking radiation, and in doing so, he confirmed Bekenstein's entropy formula. The entropy of a black hole, in precise terms, equals the area of its event horizon divided by 4 times the Planck area. And here's what's wild about that. The Planck area is incredibly tiny, about 10 to the minus 66 square centimeters, so even a modest black hole has an absolutely enormous entropy, an unimaginably large number of bits of information encoded on its surface. But think about what that means. All the information about everything that ever fell into the black hole, every star, every planet, every book, every atom, is somehow encoded on a 2-dimensional surface, not in the 3-dimensional volume inside, on the boundary. This led to one of the most profound ideas in modern theoretical physics, the holographic principle. It was articulated most clearly by Gerard 't Hooft in 1993 and then developed extensively by Leonard Susskind. And what it says is this: the maximum amount of information that can be contained in any region of space is proportional not to the volume of that region, but to the area of its boundary. The 3-dimensional world we experience might be, in some deep sense, a projection, a hologram, of information living on a 2-dimensional surface. Now, I want to be careful here, because this is one of those ideas that gets wildly misrepresented in popular culture. People hear the universe is a hologram and think it means the universe is fake, or that we're living in a simulation, or something like that. That's not what it means. The universe is completely real. What the holographic principle suggests is that the fundamental description of reality might require fewer dimensions than we think. The information content of the universe might be lower dimensional than the space we move through. It's a statement about the deep structure of physics, not about whether your coffee this morning was real. Your coffee was real. But here's where this connects back to the Big Bang. If the holographic principle is correct, then the very early universe, that incredibly hot, dense state we've been talking about all night, contained a specific, finite amount of information, And as the universe expanded, that information wasn't created or destroyed. It was redistributed, reshuffled, processed. The expansion of the universe, the formation of galaxies, the evolution of stars, the emergence of planets and life and consciousness, all of it can be thought of as the universe processing its initial information in increasingly complex ways. Think about that for a second. The cosmic microwave background, those tiny temperature fluctuations that COBE and WMAP and Planck mapped so carefully, those are, in a very real sense, the earliest information we can access. They're the universe's baby picture, yes, but they're also a data set. They encode the initial conditions from which everything else followed. The pattern of slightly hotter and slightly cooler spots in the CMB determined where matter would clump, where galaxies would form, where stars would ignite, where planets would coalesce, where, eventually, on at least one small rocky world, molecules would arrange themselves into configurations complex enough to wonder about their own origins. And this brings us to something genuinely beautiful, which is the arrow of time. You know how time seems to flow in one direction, from past to future, from cause to effect, from the egg breaking to the omelet, but never the reverse? Physicists have struggled with this for over a century, because almost all the fundamental laws of physics are time symmetric. They work just as well running backward as forward. So where does the arrow of time come from? The best answer we have, and it's an answer that connects directly to the Big Bang, is that time's arrow comes from the fact that the universe started in an extraordinarily low entropy state. The initial conditions were special. They were ordered. And everything that's happened since has been the universe moving from that low entropy beginning toward higher and higher entropy, more and more disorder. That's what the second law of thermodynamics really says. Not that disorder always increases in every local situation, but that the universe as a whole is on a one-way journey from order to disorder. And the reason it can make that journey is that it started somewhere very ordered. Roger Penrose, and we mentioned him earlier with his cyclic cosmology, has emphasized this point more than almost anyone. He calls it the past hypothesis, and he's pointed out that the Big Bang was, thermodynamically speaking, an almost absurdly special state. The gravitational degrees of freedom were smooth and uniform. Matter was spread out almost perfectly evenly, and gravity is weird, because with gravity, smooth and even, is low entropy. Unlike a gas in a box where uniform distribution is the most disordered state, a gravitational system becomes more disordered by clumping. Stars, galaxies, black holes, these represent increasing gravitational entropy. So the smooth early universe was like a wound-up clock, and everything since has been the unwinding. This means the Big Bang didn't just give us matter and energy and space-time. It gave us time itself, not the dimension, but the direction, the arrow, the reason yesterday is different from tomorrow, the reason you remember the past but not the future, the reason coffee cools down and never spontaneously heats up. All of it traces back to those initial conditions, to that first fraction of a second, to whatever set the universe on its course with such improbable smoothness. And we still don't fully understand why. Why were the initial conditions so special? Inflation helps. It explains how a tiny patch could have been smoothed out and stretched to cosmic scales. But inflation itself had to start somehow, and the question of why the pre-inflationary state had the right conditions to trigger inflation is still open. It's like peeling an onion. Every answer reveals another layer of question underneath. So where does all of this leave us? Let me try to pull the threads together, because we've covered an enormous amount of ground tonight, and I think it's worth stepping back and seeing the shape of the whole story. We started with the simple observation that the night sky is dark. We talked about how that seemingly trivial fact, Olber's paradox, actually tells you something profound. The universe can't be infinite, eternal, and static all at once. Something has to give. And for most of human history, nobody knew what. Then came Einstein, and general relativity, and the strange prediction that the universe should be dynamic, expanding, or contracting. Einstein himself flinched and added his cosmological constant to keep things still. But Friedman and Lemaitre did the math honestly and found expansion. And Hubble, up on Mount Wilson with that 100-inch telescope, saw the galaxies rushing away and confirmed it. The universe is getting bigger. Run the clock backward and everything converges. There was a beginning. We talked about the resistance to that idea, Hoyle's steady-state model, the philosophical discomfort with a moment of creation, the decades of debate. And then Penzias and Wilson, with their horn antenna in New Jersey, stumbled onto the cosmic microwave background and settled the argument. The Big Bang left an afterglow, and we found it. We found the heat from the beginning of everything. We went deeper into what actually happened in those first moments, the unimaginable temperatures, the particle soup, nucleosynthesis forging hydrogen and helium in the first few minutes, and then the long wait until recombination at 380,000 years, when atoms formed and light was set free. That light is still here. It's all around you right now, stretched by expansion into microwaves, a faint whisper of warmth just 2.725 degrees above absolute zero. We explored the problems with the standard Big Bang, the horizon problem, the flatness problem, and how Alan Guth's inflation solved them in one elegant stroke. A brief moment of exponential expansion that smoothed and flattened everything and, as a bonus, generated the quantum fluctuations that seeded all the structure we see today. We followed the satellites, COBEWMAP, Planck, as they mapped those fluctuations with increasing precision and confirmed the lambda CDM model with its strange recipe. Only 5% ordinary matter, 27% dark matter, 68% dark energy. We confronted the singularity and admitted what we don't know, that general relativity breaks down at the very beginning, and we need a quantum theory of gravity to go further. We looked at the candidates, string theory, loop quantum gravity, and at the speculative proposals for what might have come before, Hartley and Hawking's no-boundary proposal, Vilenkin's tunneling from nothing, Penrose's cyclic cosmology. We talked about gravitational waves and how LISA and pulsar timing arrays might someday let us listen to echoes from before the CMB, from the very first moments. And we ended up here, with the deep mysteries that remain. Dark matter, which we've never directly detected. Dark energy, which might be evolving. The Hubble tension, which might be pointing to new physics. And the profound question of information, whether the universe is, at bottom, a vast computation unfolding from an extraordinarily special set of initial conditions. Here's what I want to leave you with. The Big Bang isn't just a theory about the past. It's the reason the present exists. Every atom in your body was forged in the processes that followed from it. Hydrogen from the first few minutes, heavier elements from stars that lived and died over billions of years, all of it made possible by the expansion that started 13.8 billion years ago. You are, quite literally, the universe looking back at its own beginning and trying to understand how it got here. And we've made astonishing progress. 100 years ago, we didn't even know other galaxies existed. 50 years ago, we just discovered the CMB. 25 years ago, we just learned the expansion is accelerating. The pace of discovery has been breathtaking, and there's no reason to think it's slowing down. Somewhere right now, a graduate student is staring at data from a telescope or a detector or a simulation, and they're seeing something that doesn't quite fit, something that nags at them, and they're going to pull on that thread, and it's going to unravel into something wonderful that none of us can predict. That's how it's always worked. That's how Lemaitre looked at Hubble's data and saw a universe with a beginning. That's how Penzias and Wilson heard a hiss in their antenna and found the afterglow of creation. That's how a young Alan Guth, sitting alone in his office late at night, scribbled "spectacular realization" in his notebook and changed our understanding of the first fraction of a second. The universe began. It's still going, and we're part of it. Briefly, improbably, wonderfully. That's not a bad thought to fall asleep to. The whole cosmos, from that first unimaginable moment to the gentle hum of microwaves filling the room around you right now, is one continuous unfolding, one long story still being told. And you're in it. You've always been in it. Every breath you take is the universe expanding, just a little bit more, in its own quiet way. So let that settle over you. Let the numbers and the names and the dates drift away if they want to. What stays is the feeling, the sheer improbability and beauty of the fact that anything exists at all, that the laws of physics allow for stars and planets and warm blankets and quiet nights and curious minds wondering about the beginning of everything. It's all connected. It always has been. And it's more than enough to rest in.